Finish chapter 18 first, so we got a few more reactions to look at as far as 18 goes. If we want to reduce the aromatic ring, we can go through and actually force it to occur. Okay? It is something that we're going to have to force to occur because it's not a particularly easy reaction. Okay, why would it be difficult?
Because it's pretty stable.
Yeah, the aromatic ring was relatively stable due to all that resonance, so it's not easy for it to actually hook up with any hydrogens to get through the reaction. So we could go through and actually force it. We have to add that catalyst, as we do with all hydrogen reduction reactions. And then you can see your pressure goes up to 100 atmospheres. Standard pressure is 1 atmosphere. Okay, so that's what we're living in. We'd have to go up to 100 atmospheres to kind of get enough pressure to force it to react. And we're also going to 150 degrees Celsius. Okay, so it's pretty forceful conditions to actually get that to occur. Okay, so not the easiest of the reactions. It is going to be exothermic, even though it's not an easy reaction. Why would it be exothermic? You're also making bonds, though. Our alkane is always lower in energy than our alkene. Okay, so if we were going to look at an energy diagram, we would still have our aromatic, our benzene ring, higher in energy. That was a terrible looking benzene ring, but it's close enough. To our cycloalkane, our saturated structure. Okay, so it is still an exothermic reaction. The reason it's so forceful is not so much just the difference in energy between those two states, but the difference in energy with our transition state. Okay, so the transition state to actually get up and over is really your big issue. Okay, and because the aromatic ring is so much lower in energy than a standard alkene, that transition state energy is also much, much higher, okay? Or is higher relative to your alkene, okay? So the nickel would act as a catalyst and help drop that activation energy, but even still, I mean, 100 atmospheres and 150 degrees Celsius, you're still looking at pretty forceful conditions to get that to occur. Most organic chemistry is not done at those temperatures and pressures. Primarily because it's not particularly safe, because you have to deal with those high pressures and temperatures. It's also not particularly easy to go through and do. So when we're going to try and build different structures, when we get into the lab, we almost always try and pick more mild conditions, because we don't want to have to build special equipment to go through and run these reactions. That jumped a lot further than I thought it did. I thought we had a summary slide, but I guess we don't. Here, let me draw a summary slide for you. So another way that we could do our reduction is we can start with our benzene ring. And one of the other reducing agents we have was sodium metal. Okay, sodium metal can go through and actually reduce this. And we can end up with that. So we can reduce one of those double bonds. The conditions for this are a little bit more mild. But we are adding sodium metal into that process. Okay? So how does that reaction actually occur? Well, what does sodium metal bring in? What makes it reactive? Yeah, it has that one extra electron. Okay, which should give us an idea, if we're going to look at the mechanism, if we're only starting with one electron on our sodium, what kind of mechanism do you think we're going to push through? We're going to do a radical reaction. Okay? So your textbook breaks this down into individual steps. Our sodium ion can give up, or sorry, our sodium metal can give up a single electron to one of the double bonds, and that then can break away, and we do some resonance pushing the electrons away from each other. Okay, so we got that negative charge. That negative charge is now extremely basic, so it can pull off a hydrogen from our solvent. The solvent in these kind of reactions, known as the Birch reduction, will be an alcohol, so we could look at it as methanol in this case, so it can pick up that hydrogen. We still have a radical floating around, so we need to neutralize that radical. How could we do that? We can get another sodium metal to come along, give up another electron. We generate yet another anion. That other anion can again pull off a hydrogen from our solvent. Okay, we end up with our final product. Maybe they summarized it. Oh, yeah, there we go. Summarized it here. which is what I was attempting to draw out before. So some of the conditions that we're going to need, we need the sodium metal. We need a source of hydrogen ions. So that's our reason why we have the methanol there. Any ideas what's going on with the ammonia? Our ammonia is going to act as the solvent to allow for this reaction to occur. Okay. Electrons, very, very unstable species. Ammonia is one of the few solvents that actually can temporarily stabilize the electrons. So if we put sodium metal into ammonia, we can actually get a sea of electrons, of free electrons. So ammonia is kind of a neat solvent in that case. So the end result is that we get these, we lose the aromatic ring, and we now have sp3 carbons at both ends of this. Okay? So kind of nice, if we really wanted to. If we now change the structure around, and instead of starting with just a standard benzene ring, and we put on an R group, and we run that same reaction, okay, well, in the first case, we didn't really have any differences between what double bond to react with. Now, in this case, we do get a different double bond. Okay? The double bond attached to our R group is now different than the other double bonds. Why? What's that?
Is it the hindrance of the carbon the R group is attached to?
We could look at it as a hindrance effect, except what are we actually transferring in? Single electron. Are we really going to be all that concerned about a steric effect with our electron? Well, the electron's coming in pretty small, so it's probably not something contributing to it. Yeah, we've got a tri-substituted alkene versus a di-substituted alkene in the other positions. Okay, so we could look at a potential reactivity in that case. That double bond could potentially be less reactive because it's more substituted. It's a little bit weird to think of it in that case because it's an aromatic ring. Remember, the electrons are shared all the way around it. Okay? The other thing that we could look at is instead of evaluating the double bond itself, we could evaluate the transition states in each of these. Let's see, does the previous slide give it to us? No, I'm going to go 2 back in our mechanism. Our intermediate in both steps of the mechanism gives us what? Right here, and in our next step of the mechanism, come on, whoops, I was supposed to draw. And right here in the middle, again, it was what kind of a species? An anion. We have to put a negative charge on the carbon that actually reacted with this. Where is a negative charge most stable? Primary, secondary, or tertiary? Careful. Where's your anion more stable? Negative charge. Okay, so typically when we think about stability, we're looking at cations. What makes a cation reactive? It's missing electrons. So how do we stabilize it? We put larger things near it. Why larger things? What do larger things have more of? Electrons. If we move to an anion, what makes it reactive?
Too many electrons.
Too many electrons. So what do I need to do to stabilize an anion? I need less electron density around it. Okay? So if we're going to look at the anion intermediate in each of these cases, we're going to want to pick the one, as far as our thermodynamics go, based on the one that generates the most stable anion. So our primary or secondary. Because we're dealing with a ring, will we ever see the primary? No. So we're now comparing secondary to tertiary. If we go back to that R group position, is it possible to put the negative charge on that carbon? If I did, I'd have what kind of a anion? A tertiary anion, not the secondary anion. Okay, so when we go through and look at this, we want to predict something about the chemistry at that position. Okay, and a lot of that chemistry is going to depend on what the R group is. If that R group can bring in electron density, so in this case, typically R groups are referring to what atom? Carbon. To depending on how it's referenced, I typically almost always say it's anything, but in this case we're saying it's carbon. Carbon versus hydrogen, what's the difference between those? What's the difference when we're looking at size? What's making the size different? Electrons. Okay, so if we put in an R group that has a bunch of electrons, that's going to destabilize the anion. We can't get that double bond to react. It has to be one of the other double bonds. So we could pick either one of those other double bonds and go through the rest of the mechanism, and you'd see that what we end up with is our double bond, or our sp3 carbons, being aligned not along the same axis as our R group. Okay, that sounded kind of weird. Does that make sense? Okay, so the one that we don't see, the product that we don't see, is the one they're showing here, where our sp3 carbons are on the axis of our R group. Okay, we can't get that one because that R group contributes electron density and prevents the anion from forming, our anion intermediate from forming at that position, which is ultimately where our sp3 carbon was. Okay. What if we change the R group? Is there a way that we could make a tertiary carbon be able to accept a negative charge?
Give a very positive R group.
We want to put an R group on there that has very little electron density. Okay? So let's look at the next option. If we shift to something like acetophenone, okay, well, your first assumption might be, well, that looks an awful lot like an R group. That first atom is a carbon. But what's special about that carbon now in this case? That carbonyl is withdrawing electron density, making that carbon very positive. How can we stabilize that positive carbon? We can make the carbon next to it our anion, okay, or our lone pair. Which means when we go through and look at our reduction reaction, our Birch reaction, you'll notice what position is reduced. The one where the substituent was attached. Okay? And the results that we don't see are the other ones. Okay? So the R group can have a huge impact on how the Birch reaction occurs, on how it affects the dynamics within the aromatic ring. Okay? So when you're dealing with these reductions from chapter 18, evaluate whatever that group is and decide, does it have more electrons than hydrogen or does it have less? If it has more electrons, we're going to expect our sp3 carbons to form off the axis of our R group. If our R group has less electrons than a hydrogen, how do you get less electrons than hydrogen? You have to become positive. A hydrogen atom has a single electron. The only way we can get less than a single electron is to become positive. Okay? So that's kind of one of the interesting aspects of your Birch reduction. Okay, questions about the Birch reduction? The rest of this is now spectroscopy. Okay, what's another group that we could potentially put there based on the lab, or that lab quiz that we took? How about if I did
Carboxylic acid?
Carboxylic acid. What would we expect the product to be?
The same product as that.
Put our carbonyl on, our OH, except now where's our reduction occur? Occurs at that position. Double bonds are going to be on the either side of it. Okay? And again, when I was referencing that axis, because our R group has less electrons than a hydrogen, that axis is where our reduction occurs. And we get our sp3 carbons on either side. Okay? What happens if we switch that up and say, well, heck, why not? Let's just go through and do a whiteboard. What if I started with phenol? And just to be different. And I go through the Birch reduction. What do we expect of the product in this case? What's our R group atom?
Oxygen.
Our oxygen. Does it have more electrons or less electrons than a hydrogen? More electrons, which means
It's not going to reduce that carbon.
it's not going to reduce at that carbon. Our result, if we could actually push this to occur, it's a little bit weird because we've got an acid and a base in there. That carbon does not get reduced, but our double bonds on opposite sides. Does that make sense? Questions about anything with the birch? Okay. So the next part is we can move into spectroscopy. Let's see, did I put on that other summary slide? No, I didn't. Okay. When it comes to IR spectroscopy, I've noticed that a lot of people seem to have problems with this. And when the textbook goes through and explains it, they give you this, I think this was pulled from the textbook. They give you this huge range and highlight all these different areas that you can pick out as far as interpreting your IR spectrum, okay, when it comes to an aromatic ring, okay, or a benzene. So the first thing that I'd want to do here is draw out what we're looking at. We're looking at ethyl benzene. So it's a benzene ring with an ethyl group, 2 carbons attached to it. Okay? And as we've discussed, at least in the lab class, before we even look at the IR, we should identify what bonds we would expect to see. So based on that structure, what bonds would you expect to show up?
sp2 hybridized carbons.
We won't see an atom. IR never shows you an atom.
The carbon hydrogen bonds.
Okay, the carbon hydrogen, where we have sp2 hybridization. Okay, what else? We've got double bond carbons. What else? We've got carbon hydrogen sp3s. Anything else?
Technically single bond carbons.
Okay, technically we do have that carbon-carbon single bond. So I could draw that in there. So within that, we came up with, what, 4 things to look at. If we go through and look at what they've given us on the table, they've said 4 things to look at as well. Okay, so maybe that matches, except if we look at what they've gone through and labeled versus what we just identified, do they match? Did they mention anything about a carbon-carbon single bond? Nope, so that was not useful. Did they mention anything about a carbon-hydrogen sp3? Nope, also not on that list. They mention anything about a carbon-carbon double bond? Yeah, carbon-hydrogen where the carbon is sp2 hybridized? Yep, they mentioned that. Those are the only 2 bonds that I would really expect you to know. Okay? The rest of those signals, i.e. the other 2, are important. Okay? And you can do some pretty big interpretation based on those if you know anything about them. How many of you know anything about the overtone or the carbon-hydrogen bending found in aromatic rings? Nobody? Really? Okay. The only reason I know anything about it is because I didn't like IR when I was in class and spent hours upon hours in the library reading over tables and books of IR spectrum until I could see those patterns and identify them. So when it comes to your interpretive abilities for the IR, really what I would expect, go through and highlight these, your CH stretching from an sp2 carbon. And then I would actually argue that the carbon-carbon double bond is even a little bit more of a stretch, okay, for you guys to pick up. Okay, because there's other important features that you could find without having to look at that. That range starts to overlap carbonyls. So you can see some carbonyls get in the way there. You can see other carbon-carbon double bonds. So it can be a little bit more difficult to interpret. Okay, but those are your 2 primary signals that you should be concerned about when you look at IR. There are other pieces of information you can get that usually aren't worth the effort to deal with. So when you look at IR, identify those 2 main characteristics for your aromatic compounds, leave the rest of it alone. Does that make sense? So simplify. Where does the carbon-hydrogen show up for your sp2s? Just as a quick test. Huh?
In that area you don't really look at.
carbon, hydrogen, sp2. So not the bend, but the stretch. What's that number? So 3,000 is a really, really important number to know with your carbon hydrogens. If you have an sp2 carbon, that carbon hydrogen stretch shows up just barely greater than 3,000. Okay, so if you set up your line at 3,000, anything bigger than that, carbon hydrogen sp2. What's less than that?
SP3.
Your sp3s. And if we go back and take a look at what they've got highlighted in that area, you might have to look at this later on your computer. There's a yellow section that they're highlighting only half of those signals. What's the other half due to? The CHSP3s coming from the ethyl portion of your benzene. Okay? Very difficult sometimes to delineate between those. What I would typically recommend, both with the sapling homework and on exams, is get another sheet of paper and line it up along the bottom axis, because usually they've done that pretty square, and your paper is usually pretty square, and slide that along until you hit the 3,000 line. Evaluate your peaks. Is it lower than that, or is it higher than that line that you just dropped in? Otherwise, you're kind of guessing at that open space, and that can be a bit difficult to interpret. Okay? So it's just kind of how I would approach that. Other things we could look at would be the HNMR and the carbon NMR. So with the HNMR, the aromatic ring does cause a pretty massive shift of those hydrogen signals. Okay? And that's due to ring currents within the benzene. And that causes your shift to go from a standard carbon hydrogen in maybe that 1 to probably at 4 most range, all the way up to that 7 range. What else shows up in that 7 range? Okay, your silence is actually a good answer in this case. Not a whole heck of a lot else. So if you see any peaks, probably between 6.5 and 8.5, they are typically due to an aromatic ring. Okay, we can do all sorts of other weird things to cause it to shift higher in order to get standard carbon hydrogen peaks to shift higher. But if you see something there, typically it's due to an aromatic ring. Okay? If you see a signal there, you should be really, really happy on a test. Why might that be the case? You know it's aromatic, which tells you what? You now know where 6 carbons are located well relative to each other and the double bonds. That's pretty huge as far as a structural interpretation without actually having to interpret anything else in the spectrum. Just having a signal in that range gives you those 6 carbons. That's huge. Okay. We can analyze it a little bit further. What's the red 5 represent in this case? The non-amount of peaks, the amount of hydrogens. In this case, it says 5. What does that mean about my aromatic ring?
It's got a substituent.
It's got a single substituent on it, okay, at its simplest form. Of course, it could always get more complex, but at its simplest form, that gives us a pretty good piece with really ignoring almost everything else. Okay. What if you had 2 substituents on it? What would the integration be? 4, because you've gotten rid of those 2 hydrogens. How many different ways can you arrange 2 groups around the benzene ring? Is it infinite? There's 3 or 4 different ways, and you can probably get up to higher than that, depending on what those substituents are. If they're the same thing, you only get 3 ways. If they're different, you can get a couple different things, okay, a couple different options. What is that going to do as far as your interpretation goes? Well, now the hydrogens on that ring are now going to see slightly different environments, and you generate very characteristic patterns within your HNMR. Okay? So a little bit of practice with HNMR with your aromatic ring should really pick that up for you. You should be able to get those identified pretty instantly as soon as you see them. Okay? I'm not going to do any practice in class because I do feel that that is something that you should have learned in first semester. If you've got questions about it, after class I've got no problems going through and doing a whole bunch of examples. Okay? So here they went through and discussed a few different options. If we've got 2 substituents, we could align those substituents on opposite ends. So relative to each other, where are those located? Para, good call. So we're separating those on opposite sides. How does that affect the hydrogens? Well, now there's lots of symmetry within the structure. We end up with one signal. And it ends up being a singlet because since all the hydrogens are the same, none of them have any neighbors. Okay, so we can interpret, based on just seeing that single signal there, our substitution pattern of the whole ring. Okay, so it's really, really, really powerful. If you switched it up where you had two different groups para to each other, you see a slightly different setup of signals. All right? So it can be helpful to go through and interpret those. I would recommend as general practice, you start with one substituent, determine what kind of patterning you would expect to see. Then move to two and try all possible orientations and write down what kind of patterning you would see. Then switch to those two substituents being different from each other and look at all the possible patternings. It sounds a little bit daunting, but it looks like it's 10 structures. Okay, so it's really not too bad, and that can set you up to the point where you can just look at the spectrum and say, yes, that's what it is. It matches that one pattern. Okay, so it can be very, very helpful to go through and do that. Next thing that we could do is look at carbon signals. Because the ring kind of constricts everything and forces those 6 carbons to be in a particular alignment, we can actually get a reasonable amount of information out of the carbon NMR. That said, I have never interpreted the carbon NMR for aromatic signals. I would always shift to the hydrogen NMR because it's almost always provided instead of the carbon NMR. Okay, so the textbook is just giving you some extra information. They went through and looked at a variety of different arrangements. This is what I was asking you to do for the hydrogen NMR. Okay, but we can pull that same stuff out of the carbon NMR. Okay, same general idea. Questions about that? Okay. So let's take a look at this molecule. Let's predict the shift for your carbon signals, and then your shift, integration, and multiplicity for your hydrogen signals. Did I give you the answer? Oop, don't look at that. Yes, I gave you the answer. Okay, so to start it off, where do you guys want to start with first? Which one's easier, carbon or hydrogen? What's that?
Hydrogen.
I know I said I would get more information out of the hydrogen, but typically the more information you have, the more difficult it is to interpret. Okay.
Let's go with carbon.
So I would shift and do the carbon instead of the hydrogen. Okay, so if we start with our carbon, first thing we'd want to figure out is how many unique carbons we would see. So how many peaks should we expect to see? So just like or with all forms of NMR, every single atom has a signal in the spectrum. That signal might show up in the same spot as another one. Okay? And in carbon NMR, we can't count that. So what we want to go through and do is evaluate our differences. So let's pick any point. Let's pick here. That's going to have a signal. Okay, let's move to the next atom. I like going counterclockwise just to be difficult. That next atom, or that next carbon, is it different than carbon number 1? What's that?
But it's actually clockwise.
Yeah.
I just like to be really difficult. Okay, so we'll go clockwise. Okay, that looks counter. In any case, is that different than carbon number 1? Okay, why is it different? Where do you see that difference? Closer to the R group. So we got a couple different options on there. We could just say closer around that direction. The other thing that I would do is if we look directly across from carbon number 1, we see the R group. If we look directly across from our other carbon, do we see the R group? Nope. Which means they see different things, which means they are chemically different. As we continue to move counterclockwise, I like that. We could move to the next one. Is that one different from both or the other two? Yep, it's even closer to the aromatic ring. How about the next, or sorry, the substituent? How about the next one? Still different. So we continue to move. Do we expect that one to be different? No, it is different. It's the, or sorry. No, it is the same as number 3. Okay? It is one bond away from our substituent. All right, yes, one is above, one is below, but what can we do with this bond right here? We can freely rotate about that position, making both those 3's identical to each other. Continue around and we would end up with 2 over here. Next carbon. Same or different from what we've evaluated so far?
Different.
Different? How do you know it's different?
It's
Very
very different.
different. Okay, that doesn't help. There we go. That's what I wanted to hear. sp3 carbon versus sp2. Okay. Next carbon. Okay. It looks a lot like 4. It's a carbon part of the ring that has a substituent attached to it, being carbon 5. So we would expect that to be the same. What's your comment?
Also another substituent on the other side.
If we take a look at that position, when it looks across, what does it see? Another substituent. If we take a look at carbon number 4 and it looks across, what does it see? No other substituent. Are those 2 carbons different? Yes. Okay, so it may involve looking further out through the rest of the structure. Next position. Okay, different. If 6 was different, then 7 can't match up with our other ones. Next one.
No, same, sorry.
1 bond away, 1 bond away. Look across, no substituent, cross, no substituent.
What if that substituent on the right side was different?
If we went through and now changed even this to a BR, are those 7s now different from each other? Yes, they are different. Okay. How different would they be? Not a whole lot. What happens if I put the bromine closer? Put it over here. Would they be more different or less different? More different, because the difference appears closer to that atom. You should be able to go through the rest of this, assuming I can number this correctly. We get 7, 7, 5, 4, 3, 2s, and 1. I do the symmetry of that. So if we looked at the carbon NMR, we would expect to see 7 signals. Chemical shifts. 1, 2, 3, and 4. We would predict to have what chemical shift? Also known as our little delta. Where would those be? We didn't talk about this with our carbon NMR yet. What's that?
100 to 100.
How do you know it's 100 to 150? There's a little bit better of an answer than that. It's not much better. You would have to have some recall on where your alkene, your carbon-carbon double bonds, show up. That shows up in the range 100 to 150. Where does carbon 5 show up? That's looking at a standard alkane. Your standard alkanes typically show up, I think, 0 to 50. Where's carbon 7 going to show up? Carbon 7 is a carbon part of an aromatic ring, right? How about carbons 1, 2, 3, 4? What are they part of? Where would we expect carbon 7 to show up? 100 to 150. Okay? So what we're trying to do is take advantage of those bulk ranges with our carbon NMR to come up with an idea. Can I steal that from you, Josh? Oh, this isn't what I thought it was. There are simplified tables that are floating around. I would highly recommend when you look at carbon NMR that you look at the simplest table possible. And I would argue for the table that you've got here, it's more complex than it needs to be. If you take a look at the spectroscopy background packet that I posted to Canvas, there's a modified version of it on that site that gives you a much, much shorter section. You look at alkanes, alkenes, and carbonyls. That's it. As far as your carbon NMR goes, those are really the only three characteristic ranges that you can find. Okay? So that gives us our carbon NMR. What happens if we go through and do our H NMR? First thing would be helpful to do, draw on the hydrogens. Yes, it's that thing. For our hydrogen NMR, we end up seeing only 5 signals. Why only 5? We still get the symmetry that we had with our carbon NMR. Why do we see less than we did with our carbon NMR? Well, in our carbon NMR, we had 2 carbons that had how many hydrogens attached to them? 0. So we shouldn't expect to see the same number of peaks between our hydrogen and our carbon. Okay. You should be able to process this a step further because that gives you just the number of peaks. You should be able to do chemical shift. For this guy, we would expect our 7 range. For this hydrogen, we'd expect, probably about 2. I don't know why that looks like a 77. The next thing you should be able to do is predict the integration and the splitting patterns. Okay, because that's going to, well, I'll do it for one of them. No, I can't do it for one of them. Math is too hard for me. Okay, we would go through and count how many, well, no, it's not. Count how many hydrogens are represented by it, sorry. How many hydrogens are represented by our 7 shift? How many hydrogens are just like it? 4. So we would expect an integration of 4 for that one. How many neighbors does that hydrogen have?
1.
You're saying that neighbor? Is that what you're saying was the neighbor, the one I just drew in there?
Yes.
Now in orange?
It's not.
But it's not because,
It's on a different card.
nope. It's chemically the same. It may be a hydrogen on a different carbon, but chemically it is exactly the same. They see exactly the same environments. If it's the same, we see no splitting, and what we see is a singlet for our splitting pattern. Okay? The homework goes through or has you do a couple different breakdowns like we're just going through here, and also analyzing full-on spectra as well. You should be able to go through and predict the rest of this spectrum. The answers are provided on the next slide. That's going to give you some information, unfortunately not as much as I would have liked. It'll give you the information about your chemical shifts, how many signals you see. It's not giving you the integration. Oh, it is giving you the integration. I do see that. It's because they all overlap. They're not being particularly nice with those answers. I'll go through and post answers to everything that you should have predicted would have occurred. One of the big issues with this for A, B, C, and E within the HNMR, you'll notice the splitting pattern says what? Multiplet. What does multiplet mean? It means it's a freaking mess. Okay? Multiplet can mean all sorts of different things, but typically it means there's so many different peaks that we can't interpret it. So what they've given you here is not the theoretical spectrum, but the actual spectrum information. So the signals for A, B, C, and E are so similar to each other that those signals overlap and turn it into a cluster F of a mess. Okay? So what I'll go through and do is tell you what those should have actually come out at, and you can compare what they should have come out at with what you've come up with. Okay? And I'll get that posted to Canvas so you've got access to that. Why would they show up all on top of each other? What was that?
There's not much difference.
There's not much difference between those individual hydrogens. They're all attached to an aromatic ring, and they've got a certain number of substituents around them. So we're looking at effectively the same chemical shift, just slightly off, which then makes all the splitting pattern impossible to interpret. Yeah.
So is it going to split a whole bunch because HA is also the same as down here?
HA will be split by HB.
But
HB will be split by HA and HC. HD will get split by nobody. HE will get split by nobody. Did I do HC? HC will get split by HB. because they're all effectively in the same range, all of those splitting patterns overlap each other and you can't see a difference between them. That's all it's really coming down to.
So if you only look at like that one half, you wouldn't have to look at the other side as well?
You wouldn't look at the other side because
I mean, they're the same.
they're chemically the
Which
same.
is intensified.
Yep, so the integration gets bigger. So you would expect more signal underneath. All right, so that is the end of chapter, oh crap, not the end of chapter 18. There's a couple random things that we just can kind of mention about this. When we're looking at benzenes, one of the common things that pops up are graphite and buckyballs and even nanotubes, because what you've got in those cases is benzene rings all linked to each other. So you get these massively aromatic structures, which becomes chemically, I guess not chemically, synthetically pretty interesting for science. Why would that become interesting? What happens to an electron on one side of that pi system? What can it do?
Go all the way to the inside?
It can jump all the way over to the other side. Why is that kind of neat?
Very, very stable.
Stable. What's your thought?
I don't think it's right.
If instead of making those carbons, let's make them all copper atoms. What happens if they were all copper atoms? What can we do with those electrons? We can push electric current through it. Why do we use copper for all our wires? Is the electrons, we get a sea of electrons that moves from one position to another. In the case of these graphite sheets, what's nice about that? We've got a sea of electrons where we could potentially push electric current all the way through it. Why is that even more bizarre? Carbon is a non-metal. Should we be able to push electric current through carbon? You wouldn't think so. Okay, so it's an active area of research because of that resonance capability. There is a strong possibility that we can actually start to use carbon as a wiring system, okay, to generate those electric currents. So it's kind of neat in that case. Okay? You have to have it aligned perfectly and have it set up as a consistent unit. The reason why graphite doesn't work super well is because graphite has layered sheets. It's not a single sheet that goes perfectly across. And we'd need that if we're going to try and push the electrons. Okay? An electron within this sheet can jump anywhere within it as long as it's attached. But to jump to another sheet of graphite requires a jump that there's nothing there for it to move through. Okay, so we would need some way to draw out these carbon structures to keep them as one infinite sheet, okay, or as long as our wiring needed to be. So graphite's kind of neat as far as a theoretical process of that. Another way we could look at carbon is switch it into buckyballs, and we can now look at a sea of electron moving around the buckyball system. So you may have heard of buckyballs before. You take 60 carbons and you can arrange them into a soccer ball. Okay? You can scale that upwards as what they're trying to list there. You can get up to 70 carbons. You can see how important I thought this slide was, and I went through and fixed the text. It's just an interesting observation. The last one, which gets back to our electrical wiring, we can generate nanotubes, okay, or cylinders. This becomes helpful because we can now generate this conduction ability. We can push electric current from one end of the nanotube to the other. Okay? Big problems with that? How much control do we have over a single carbon atom to make sure it goes into our nanotube perfectly? Don't have very good control over that yet. So there is, like I said, active research in making individual carbon nanotubes, but we don't have the control that we would need to be able to use it as a conductive pathway, at least not yet. Okay? Places like Intel and others, I'm sure, are doing research on this, because now you're making wires instead of several microns thick down to probably the nanometer scale. Okay, so it's really, really cool to be able to push the electric current through that, so it's kind of neat in that process. Okay? So it's just kind of something fun that we could mention. Questions about anything within chapter 18 before we do 19? Okay, so 19 is all about looking at the reactions of benzene. There's three primary reactions when we're looking at our benzene reactions. We've got EAS, which is the huge one that's going to show up everywhere you look for reactions for benzene. okay, known as electrophilic aromatic substitution. The other two, okay, one of them you might be able to guess. Well, is an aromatic ring. It's also a substitution. I said it's substitution, though. How about nucleophilic aromatic substitution? So that's one of our other options. And the last one is an addition type reaction. It's an addition elimination. Okay? So what's going to happen when you add something and then eliminate? Effectively, you're doing a substitution as well. Okay? So we get those three main mechanism types. We're going to spend most of our time looking at the EAS reaction because that's probably where most of your questions will come from. And then we'll talk a little bit about the other two mechanisms as well. Not today. All right, so let's piece this together. Let's take advantage of the name and see what we can generate. What does electrophilic mean? What's positive? Okay, so I agree, electrophilic tells me we absolutely have a positive. But what's positive? Okay, well, this is in what chapter? We're looking at benzene, right? But aromatic would suggest the benzene ring, right? So if I've got them colored differently, what's positive? How about an electrophile? So let's pick E for our electrophile. All right, the last part of the name says what? Which means we're going to run a reaction, and in the course of that reaction, we're going to have to substitute something. Okay, well, E, there isn't really a whole lot to substitute within E, because that E could be virtually anything at this point. What we'd now be left with is what's going on with our benzene ring. What atoms are in our benzene ring? Carbon and? What do you think we're going to substitute? Okay, so we've heard both answers here. Why did you say hydrogen? Carbon is embedded in the middle of that structure. If we go through and put on our hydrogens, okay, more than likely, what's the first thing that's going to interact between these two objects, our electrophile and our benzene ring? Hydrogens on the outside, most likely thing to butt up against it. Okay, that doesn't mean that's what is happening. How many bonds would we have to break to substitute with our hydrogen? 1. How many bonds would we have to break to substitute with our carbon? 4 bonds to go through and break with that. Okay, that's an awful lot of bonds to try and break a carbon out of there and substitute it back in. Because not only is it breaking 4 bonds, then what do we have to do? We'd have to then reform those 4 bonds with our electrophile. Okay, so more than likely, when we're looking at our EAS reaction, what we would predict for our product would be our benzene ring again, except now we would have the electrophile attached. And what would be floating off? Hydrogen. Okay, and I liked your answer, I think, better in this case. Josh, why not just hydrogen?
It was neutral when it was attached to the aromatic ring. So.
When we pop that off, it's going to have to become H+. Okay, it will be a proton, hydrogen ion. Okay, and there's multiple reasons we can go for on this. Where did that hydrogen come from? Where was it originally found? Attached to, be more specific, not just attached to the ring, attached to carbon. What's the difference in electronegativity between carbon and hydrogen? Carbon's more electronegative, not way more. So what does that mean about the electrons between the carbon and the hydrogen? They spend most of their time with carbon. So if we break off the hydrogen, more than likely its charge should be positive. So we can do an electronegativity argument. Another argument that we can make, usually rarely looked at, okay, and this works if you're dealing with resonance as well. Take a look at your overall charge on your reactant side. What is it? Positive. In the course of a reaction, can we create or destroy matter? Nope, which means if we start with a positive, what does that mean we have to end with? Also has to be positive at the end. So that hydrogen had better come off as an H+, otherwise we've got an issue. Okay, or a Nobel Prize. Okay? So that's kind of our fundamentals of our EAS reaction. So now the things that we want to evaluate would be how this reaction works. I don't remember if I left myself enough space. I didn't leave myself enough space here, so I'm going to redraw it. Okay, so we're going to start off with our electrophile again and our aromatic ring. All right, we know where we're ending. We know we have to somehow get to this, and I'm sure you guys will give me a hard time for this as we go through and do it, but we'll discuss why I'm okay to do it this way anyway. What do you think the first step of this reaction is going to be?
Create the electrophile.
Electrophile is already generated, it's positive. So when we look at more details of the reaction, yes, we'll need to create the electrophile. At this point, I'm already saying you've got it. It's E+. So we're going to have to get that E+ to react somehow with the ring. Well, what's the charge on our E+? Positive, which means the ring needs to supply what? Negative. Where's there a negative in the ring? In a pi bond. Why the pi bond and not say in that carbon-hydrogen bond? You're right, if that helps. I could accept that. We could go based on our carbon-hydrogen bond not doing much, typically like an alkane or even an alkene. Okay. What's our reasoning behind, well, yeah, go with that. What's our reasoning behind why our alkanes don't do much?
There's not much difference.
There's not a whole lot of difference between our atoms, so we don't generate any polarity with it. You brought up another issue. What type of bond is there between our carbon and our hydrogen? Sigma bond. What do we have in the double bond? Pi electrons. Which is higher in energy, pi or sigma? Pi. So it makes sense for us to pull our pi electrons out to go through and do our reaction. All right, so we just draw that single arrow coming out just like we would do with the first step with our alkene reactions. Exact same idea. All right, the end result of that. We can put our electrophile on there. Well, actually, before I do that, do we do anything to either of the other double bonds? No. How do we know we didn't do anything to those other double bonds?
They're still there at the end.
No, I would argue we could run that argument if I got them drawn on, but I didn't draw them on yet.
If you move them, it's just going to move the negative charge around the ring.
Did we move them, though?
I'm just saying there's no point to.
Okay, true. But did we? What I want you guys to focus on is with your mechanisms, beginning to end. Okay, what did you show happened? One pi bond reacted. Did the other pi bonds do anything? No, which means when we draw out our product, what should we do with those other pi bonds? Draw them in the exact same place. Because you did not show any arrows affecting those pi bonds. Until you show me an arrow that those pi bonds do anything, they must be left alone. Alright, so now we can go through and draw in those pi bonds. Now with that other pi bond, what did we do with it?
Usually form the bond of the electron.
We took those two electrons, we took them out of the pi system, and we made a bond with our electrophile. Okay? So did we make the bond, say, here?
Is it kind of like an epoxide bond?
No, we don't even get that. Well, that's an interesting idea. Could potentially see something along those lines. What do we form a bond between?
The electrophile and one of the carbons.
An electrophile and our carbons. Is there a difference between the carbons? No. Since there's no difference, does it matter which carbon we put the electrophile on? No. Okay, so in this case, we can put that electrophile wherever we want between those two carbons. Do we now have our final answer? No, why not?
There's hydrogens.
Okay, I actually like that you're mentioning the hydrogens, so I'm going to go through and draw those all in. Okay, while I'm doing that, is there another reason why there's something wrong with it?
Well, that carbon
We will still miss that pi bond though, because we took that pi bond out to make the sigma bond with our electrophile. What were you saying, Josh, about the...
Doesn't another carbon want to have a charge?
Yeah, what's wrong with this other carbon?
Positive charge.
We took 2 electrons from the pi bond. One of those electrons came from each carbon. We take both those electrons away, and we put them both back now on one of those carbons. What happened to the other carbon?
Positive charge.
It lost electrons. It must be positively charged. How else could we have identified that we were missing something?
Doesn't have enough bonds.
Could look at not enough bonds, except the problem with that is that assumes that you drew all your hydrogens in. How many of you are drawing all of your hydrogens in each of your structures? That's kind of what I thought. So not having enough bonds is a bit questionable of a move because you'll more than likely forget to put in your hydrogens. Okay, there's another big thing, though, that comes back to that.
You can't create or destroy charge.
We cannot create or destroy charge. We just talked about that. What's our charge to begin with? Positive. What's our charge need to be when we end? Must still be positive. So since we haven't accounted for that part, or we hadn't accounted for it yet, that means there has to be a positive charge in that structure somewhere. We're missing something. We have to address that first. So now that we've got our positive charge in there, we've got our structure. So, Kirsten, what you may have been talking about is we lost the double bond. Why is that a problem?
Because we have a double bond at the end.
So we could look at the double bond at the end. Why else is it a problem? All right, it's comparing.
Aren't being shared between the 2 carbons.
I kind of like that idea. Why do we care about it being shared?
It's not uranium, it's not aromatic.
There's the word. It's not aromatic anymore. When we look at our starting material, that's aromatic. We look at our product, that's aromatic. We look at our intermediate, not aromatic. Right? That first step has a ridiculously high activation barrier, because what are we doing? We are destroying aromaticity within that ring. Okay, so why on earth would we even bother to do this reaction at all then? There has to be something making this structure somewhat stable, allowing it to form. What is that something? Resonance. What's the most unstable thing with that structure?
Positive charge.
Positive charge. How do we stabilize positive charge?
Negative.
With electrons. Highest energy electrons in this structure? In the pi bond. So, let's move those electrons towards it. What did we do to the electrophile?
Nothing.
Nothing. What did we do to any of the other hydrogens?
Nothing.
Nothing. Which means, oh man, I really should have drawn all the hydrogens. Whoever suggested I draw all the hydrogens, thanks. Appreciate that. What happens with our new structure? We finished?
You still have to put the positive charge.
We need the positive charge. Where do we put the positive charge? The bottom carbon. Very, very easy to lose that positive charge or think that you're moving the positive from carbon to carbon. Why is that a big problem? Do we move the positive charge? First off, do we ever move positive charge? No. Second off, if we move it from carbon to carbon, if you think along those lines, your gut response is going to be moved from the positive charge to the carbon. Does that carbon ever pick up a positive charge? No, it only goes to the next one. So move the electrons, follow the charges, or balance your charges after the effect, or after that fact. Okay, so cool, we've got a resonance structure that helps stabilize it. That's nice. Okay, is it a stable structure yet? Glad I gave myself lots of space. Okay, so what do we have to do?
I draw the next resonance structure.
We want to come up with the easiest way to stabilize it first. So you're talking about bringing in the hydrogen. We're going to need to do that eventually, but we don't want to do that yet because there's still higher energy electrons. Where are those higher energy electrons?
Next pi bond.
And the next pi bond over. All right, this is going to get a bit tight here. Oh, and I had to do it on the very last one too. Arguably the most important one. There's our electrophile. There's our hydrogen. Hydrogen, hydrogen, hydrogens. Freaking hydrogens. There's our double bond. What's missing? Positive charge up on that carbon. Okay? Now we've got an issue. It's still positively charged. Do we have anything there to stabilize it? Okay? We don't have any high energy pi electrons anymore, so we're going to have to find an electron source somewhere else. So we could think about going into the solution, except what do we have in the solution? We have a bunch of electrophiles. Those are positive. So the electrophiles aren't going to help us. We have to find that electron density somewhere else. Where can we find it? Josh? We can pull it from an adjacent hydrogen. And we're going to pick a very particular adjacent hydrogen.
The one on the same carbon as the electrophile.
The one with our electrophile. Why pick that hydrogen and none of the others?
If you pick the one with the positive charge is the one still going to have not enough electrons.
So if we pull the hydrogen, which I can go through in color blue, if we pull our blue hydrogen, we're still short electrons on that carbon. Okay, those electrons were already there on that carbon. That's not going to help us. Another big issue is that the electrons and that positive charge are in perpendicular orbitals. I know I keep mentioning this. It's not easy to see, but we can't bring those electrons in to stabilize. Okay, so that doesn't help us. The other option would be to drop all the way down to the green hydrogen now. Okay, except if we did that, what's the problem there? That carbon becomes sp. We need a bond angle of 180. That's bad. There's another big issue with it. No, it does fix the positive charge issue.
We don't go back to aromatic, so.
It didn't become aromatic. Okay? So our black hydrogen, the one that we actually drew on here, is going to be the most important hydrogen to remove, not only because all the other ones are bad options, but we also restore aromaticity within our structure. Okay? So that's a huge advantage to pulling that hydrogen over any of the others. Okay? So this is your overall mechanism for an EAS reaction. Guaranteed, I am going to ask you to draw an EAS mechanism on the test. Okay? 100%. I'll probably adjust it, make it a little more difficult, but you will be drawing something along these lines. Things that we need to address and make sure that show up. Well, good thing, curved arrows should show up. Charges should show up. Any intermediates should show up. Let me skip intermediates for the moment. Our product and our reactant should be good things to show up in that as well. Those will probably be given to you. The one that I kind of skipped over there would be our intermediates. How many of these intermediate structures should be drawn? Every single one of them. When you draw out a mechanism, you need to supply all resonance structures for every single step. Okay? That is the goal of a mechanism, to explain how the electrons move, always. Why did we draw the intermediates to begin with? Why did we draw the first intermediate? What was the reason behind that? Was that structure stable? Our first resonance structure? First one wasn't stable, so what did we do? We took the highest energy electrons. Those highest energy electrons happen to be pi electrons, and we drew resonance. Why do we always start with our highest energy electrons? They're going to react first, which means when you draw out a mechanism, you need to account for using your highest energy electrons first, and then slowly use your lower energy electrons as needed. Okay? That can help you cover all of the possible intermediates, because each of those potential resonance structures could have generated a different product. In this case, it didn't, but if you look at your other reactions, they could potentially. Which is why when we do the substitution reactions and you see a secondary carbocation, your first response is not to do the substitution, but to do a rearrangement or resonance, because that can cause your nucleophile to come in at a different position. Okay, so we always want to evaluate our highest energy first, then deal with the rest. Okay? These structures are so important in the EAS reaction that we give them a special name. Okay? And they're almost always got brackets around them. Anybody got a name for them? That's publishable on YouTube? Way to cheat on that. Yes, they are known as sigma complexes. Why are they sigma complexes? Kind of, sort of. We have sigma bonds in all of our structures, though. What's special or what's different about each of these resonance structures in comparison to, say, our starting material in our product? It's a big hint. It's now been... Our aromaticity is gone, and it's gone because of what atom? It's not the electrophile that prevents aromaticity. It's the carbon that has the electrophile on it. And it's not the carbon with the charge, because we can still push electrons through a positive charge, okay? Because that carbon is sp2. What's the hybridization of the one with the electrophile attached to it? sp3. Can we push electrons through an sp3 atom? No. We've lost resonance at that atom. What bonds do we have at that atom? What types of bonds? They're all sigma bonds at that atom. There's our sigma complex name. Okay? That's why it's coming out. When we go through and look at the speeds of a reaction, which I haven't figured out the best way to organize it, you're going to have to come back to these sigma complexes, because the sigma complexes are going to allow you to predict where your electrophile substitutes. Okay? Without the sigma complexes, really all you're doing is guessing. In the case of benzene, all of those hydrogens are the same. But if I go through and change one of those hydrogens to a different atom, now are all of those hydrogens the same? No, they're slightly different. That difference has an effect on where the electrophile can actually attack, just like we saw with the Birch reaction, or the Birch reduction, I should say. Okay? No, we can do it on the next slide. Okay, so our basics. We've got our aromatic ring and our electrophile, and we can generate our product. Okay, and I'm not drawing all of those things on again. Okay? If we go through and change one of those hydrogens to now, let's just make it an R group. Okay? We draw on our R group, our electrophile can now go to each of those positions. Are all those positions the same? No. What makes them different?
Proximity to the R group.
Proximity to the R group. So this first one up here, what could we number that position? That would be position
2.
Why 2, not 1? The R group is at position 1. That's where we started. So that could be called position 2. What about the position on the other side? Effectively the same thing. So we could call that 2. And if we're going to number, we'll call it 2 and 6. Chemists don't like numbers. We like giving things names. What name do we give that position? Ortho. Chemists don't like words. We come up with symbols. Next position down. We've got position 3 or 5. Don't like numbers. Meta. Don't like words.
What makes you people are communicating grunts?
Maybe after this semester. 2, 6, our last position. 4, para, and P. I'm not going to lie, I've had plenty of conversations that degraded to grunts. Okay? So we've got all of those individual positions. We're going to need to be aware of those when we propagate a little bit further into this. Now that we got the basics of what makes up our aromatic ring, those individual positions, and we have an idea of the mechanism, of course, if we're going to go into the lab, what's the first thing you're concerned about? You step in the front door of the lab, and the very first thing you think about is? Really? Safety? I'm not grading you. Let's try that. How fast can you do it? When can you get out of the lab, right? Safety. Wow. That's the perfect answer. If somebody else was grading me, that would be the answer I'd want you to give them. No one's grading me yet. So, okay. So we want to make it faster. So how can we make our reaction faster? Well, to do that, we need to know what we're starting with. So when we look at our reaction, look back to the beginning. What are we reacting? An electrophile, I like. So you may have gotten lucky starting with that one. An electrophile, we could say pi bond. I want to take it a little bit further. Let's go general, broader terms. What were you saying?
Electrons in the pure orbitals.
No, even broader.
Benzene,
Broader.
Aromatic ring.
Broader. What do electrophiles react with?
nucleophile.
Nucleophiles. To get our reaction to work, we have to have a nucleophile and an electrophile. In the case of the EAS reaction, our nucleophile is the benzene ring, and our electrophile is whatever extra piece we want to put in there. If we want to make the reaction go faster, what do I need to do?
Make it a better nucleophile with electrophile.
So catalyst is a good idea as a final answer, but more generally, what we want to do is make our electrophile more electrophilic, or make our nucleophile more nucleophilic. What charge does our electrophile need to be?
Positive.
Positive. What does our nucleophile need to be? Negative. So if I want to speed up the reaction, I need to make the benzene ring more negative. If I want to speed up the reaction, I could go and look at the electrophile, make the electrophile more positive. If I can force those things to occur, my reaction should go faster. You had a good point on bringing in a catalyst. Catalysts work great to make our electrophile more positive, because catalysts can come in and take electrons away. If we take electrons away, naturally becomes more positive. How do you make the nucleophile more negative with a catalyst? We have to put more electrons into that structure, right? How many bonds do each of those carbons have? 4. They have their octet satisfied? Can we put more electrons into those carbons? No. We can't add a catalyst to affect the nucleophile. To change the characteristics of the nucleophile, we must actually change the structure of the nucleophile itself. And that is what's going to allow us to speed the reaction. We're looking at our nucleophile. Our electrophile we can do with a catalyst. Nucleophile, we have to change it. Okay, and we'll look at the example on changing, I think, with the next slide. What were you about to say?
Is that where you put like a halogen?
Okay. So affecting the nucleophile, I'm going to do this real quickly. If we want to speed the reaction, we will come back to this. I might even start, well, I'm not going to start here next week. We'll come back to it. What's the big difference between our benzene ring and that top structure? And I take it a step further than a partial charge, or a step easier. It's not an H, it's X. What can you tell me about X? Okay, that halogen answer, I would understand why you're coming up with that, but I'm using X as a variable in this case, not as a halogen. So X, in this case, has lone pairs. What's special about a lone pair? It's a lone pair of what? Electrons. What did we need to make our reaction go faster? Electrons on our aromatic ring. What can we do with electrons on that X atom?
Move them into the ring.
We can do resonance, move the electrons into the ring. First arrow, we move them down. How many bonds does that carbon now have? So we can draw it out. We got that structure. Okay, with our X being positive. Why does the X need to be positive?
Took electrons away from it.
Okay, we took electrons from it. The problem with that carbon now has 5 bonds. Instead of now panicking, saying, okay, everything we did was wrong, what that means is we now have to go back to our first drawing and say, okay, we made too many bonds around that carbon, which means I have to break a bond. When dealing with resonance, what bonds are you allowed to break? Pi bonds only. So we either break the pi bond we just made or break the other pi bond. So what we're going to do is, because we started moving atom to bond, when we move our next set of electrons, we will move from the bond to an atom. So when we draw out our result, wow, I can't believe I was able to erase that nicely.
Then we could do negative carbon.
What happens to that carbon? It's now negatively charged. What did we need to do to speed the reaction? We need to make our aromatic ring more negative. What did we just do by putting on a different group other than hydrogen?
Make it more nucleophilic.
We made our aromatic ring more nucleophilic. Okay? So we can speed the reaction by making our nucleophile more nucleophilic by changing one of the atoms on the ring. Okay? Yes, changing those is not the easiest thing to do, but we'll discuss that. Okay? Once that atom is changed, we can speed our reaction. For that to speed, or that speeding to occur, what does X need to have? It needs to have extra electrons. And in particular, we could go based on the lone pairs. There's a broader definition in this because I could have just as easily, instead of doing that X with a lone pair, I could have done that as a CH3. CH3 would speed the reaction over benzene. Toluene reacts faster than benzene. Why? Atom X doesn't have any lone pairs. What's the difference?
That carbon's pulling in electron density from the hydrogens.
Kind of, sort of. How does that affect the ring if it's taking electrons from hydrogens?
Still get that potential for resonance.
It's not officially resonance. It's an inductive, pseudo-inductive effect in this case. The big difference is carbon has more electrons than hydrogen. Atom X, as a rule, isn't that it has lone pairs, it's that it has more electrons than a hydrogen atom. How many electrons does a hydrogen atom have? 1. Okay? So pretty much any atom has more electrons than hydrogen. What's the one case where you don't have more electrons? If you have a positive charge. Okay, either formal or partial. Okay? That is all I'll talk about for the aromatic ring, making it more reactive at this point. So Tuesday, Wednesday, Monday, we'll start with our electrophile. Okay, we'll look at how we can speed up the reaction by looking at the electrophile. We'll then look at a whole bunch of reagents for our electrophiles, and then we'll go back to the nucleophile, look at some of its chemistry again, like we just evaluated here. So evaluating those resonance contributions, and then you're pretty much into the new reactions, okay? The other reactions, the NAS and the addition-elimination reaction, okay?